Good morning, student. Today we are going to discuss about the packing efficiency in simple cubic arrangements. First, how we can get the simple cubic arrangements. So we can get the simple cubic arrangement, the AA type of two-dimensional arrangements in three dimensions. Spheres in one layer sitting directly on the top of the previous layers. Here, all the spheres are aligned vertically and horizontally. Here all layers are identical. In simple cubic arrangements, each sphere is in contact with a 6 neighboring spheres. The coordination number of simple cubic arrangement is 6a. What is a coordination number? So number of neighboring atom is called a coordination number. Here 4 sphere in its own layer and one above and one below. So in this way we can get the simple cubic arrangements. Here you can see this is the AA type arrangements. We arrange the two-dimensional AA type arrangements in 3 dimensions. Okay, in 3 dimensions. Here the sphere of second row directly sitting on the top of the previous or first layer. The sphere of the second layer directly sitting on the top of the first layer. So we can arrange this type of sphere in 3 dimensions. So we get a simple cubic arrangements. Simple cubic arrangements. Here you can see the coordination number is 6. Coordination number is 6a. 4 sphere in its own layer and one above and one below. Here this is the 4 sphere in one layer. So one sphere in the upper layer, one sphere in the bottom layers. So in this way, here the coordination number of in simple cubic arrangement is 6. The coordination number simple cubic arrangement is 6. Okay, 4 sphere. This is 4 sphere in the one layer, one sphere in the upper layer, one sphere in the lower layers. Okay, so in this way the coordination number of each sphere is 6 for simple cubic arrangement. Now let us see the packing efficiency. The packing efficiency or packing fraction is nothing but it is the fraction of atoms occupied in an unit cell is called a packing efficiency. The packing efficiency is equal to total volume occupied by sphere in a unit cell or volume of the sphere into 100. Here the packing efficiency is equal to volume occupied by effective atom into volume of the sphere by volume of unit cell into 100. So we can write the formula packing efficiency is equal to Z is the number of effective atoms 4 by 3 pi r cube by a cube. This is the volume of the unit cell is a cube into 100. This is the formula for the calculation of packing efficiency. Now let us calculate the packing efficiency in simple cubic arrangements. So in simple cubic arrangements we know that the atoms are present at the corners. In simple cubic arrangement the atoms are present at the corners. Here the atoms are present at the corners or touching along the edge of the cube. The atoms present at the corners are touching along the edge of the cube. This is the edge of the cube. The atoms present at the corners are touching along the edge of the cube. We do not touch along the diagonal of the cube. Okay. Here now we can calculate the packing efficiency in simple cubic arrangements. First we take let the edge length edge length be A, volume of the unit cell, volume of the unit cell, the volume of the unit cell is equal to length into breadth into height. Here the edge length is the A, so here length, breadth and height all are A, so we can write this A into A into A is equal to A cube. Let R is the radius of the sphere, radius of the sphere. Then we can relate the radius and the edge length. So here the radius is the R, this is a 1 R, this is a 1 R, so total 2 R. So edge length A is equal to 2 R, R is equal to A by 2, R is equal to A by 2. For simple cubic arrangements, R is equal to A by 2. So now we calculate the packing efficiency in simple cubic arrangements. Step 1. In first step, we calculate the number of atoms in simple cubic arrangements. Number of atom in simple cubic unit cell or in simple cubic arrangements is equal to, here in simple cubic arrangement the atoms are present at the corners only, so they are sharing by 8 neighboring unit cell. So number of atom in simple cubic unit cell is 8 into 1 by 8 is equal to 1. Number of atom in simple cubic arrangement is 1. Okay. So second step, step 2, we calculate the packing efficiency. We know that the formula for the packing efficiency is equal to Z into 4 by 3 pi r cube divided by A cube into 100. Here the number of atom for simple cubic unit cell is 1, so 1 into 4 by 3 pi r cube divided by A cube into 100. We substitute the value of R here from this value, so 1 into 4 by 3 pi, so R is equal to A by 2 whole cube divided by A cube into 100. So we can calculate now, we can simplify this. Packing efficiency is equal to, so 1 into 4 by 3 pi, so we cube this, A cube divided by 8, so whole divided by A cube into 100. We simplify this, we can get, so 1 into 4, this 3 goes to denominator, 3 into pi into A cube into 8 into A cube into 100. Here this A cube cancel out, then 1 4s are 4, 2 4s are 8, so the remaining part is pi by 6 into 100. We substitute the value of pi, 22 by 7 into 100, that is into 6a. So we simplify this, we can get 2200 divided by 42. So we get 52.38%, or we can simply write 52.4%. Okay, this is the volume occupied by the spheres. For vacant space is equal to 100 minus 52.38 is equal to 47.62%. Okay, in this way we have to calculate the packing efficiency in simple cubic arrangements. So now let us see the summary for the simple cubic arrangements. So the packing efficiency in simple cubic arrangements. So the number of atom is 1 for simple cubic arrangements. The packing efficiency is 52.38, or we can say 52.4% approximately. Here vacant phase is 47.62, so approximately we can say 47.6%. The coordination number is 6. So in this way we have to memorize this data. So it is very important for the NEET as well as JEE exams. Thank you, student. I hope you understand how we can calculate the packing efficiency in simple cubic arrangements. Thank you, student.